Okay, so in this lesson, we are going to look at reflections. We will look at reflections in the x-axis, reflections in the y-axis, and the reflection on the line y equals x, which is also called an inverse. So let's start with reflections on the x and y-axis. And actually, I'm going to start by just writing that transformation equation out that you should have in your formula sheet, so that I can talk about a few different things. Actually, it's already here. Okay, good. All right, so we're gonna just make a list here. So last class we talked about the A value here. So we know that our A value is a vertical stretch along the x-axis. Okay, or sometimes you'll see it called the line y equals 0, which is the same as the x-axis, but you will see those two different terminologies or way of saying the x-axis. Then we're going to leave a little space. We know the B value is our horizontal stretch of 1 over b, right? We always take that reciprocal along the y-axis, or the line y equals 0. X equals 0, sorry. Okay, and then we talked about how the h value is going to be our horizontal translation, so it's going to move the graph left or right, and the k value moves our graph up or down. Okay, so what we're adding here is reflections. So what that means is if you have a negative a, so it means you have a negative in front of that function, okay, you're actually going to have a reflection on the x-axis. Notice how it matches what we've stated before. And that only makes sense, right? So if our a value is, say, -5, it means I'm vertically stretching that graph by 5 along the x-axis, but it also means I'm reflecting that graph along the x-axis. Okay, and likewise, if we had a negative b, it would mean a reflection on the y-axis. And again, you'll see instead of y-axis, sometimes they'll say the line x equals 0, and you just need to realize those are the same things. Okay. Something else I'm going to point out really quickly here, grab my highlighter, is anything outside of that function notation, okay, that is going to affect my y variable. So when you're working with mapping coordinates, and we've talked about mapping coordinates in our last lesson, okay, so anything outside of that function notation is going to affect my y variable when it comes to mapping coordinates. Anything inside that function notation, so in those brackets, is going to affect my x variable when it comes to mapping notation. All right, so let's actually look at and see what a reflection would look like. So notice how the negative is outside. So that means if it's outside the f function, that's your a value, right? So it means we're going to have a reflection along the x-axis. Okay, so if I were to take a highlighter here, here's my x-axis, it would pretty much just be like that x-axis becomes a mirror, and I'm just flipping that graph over that mirror. So once again, we do have invariant points. So invariant points are going to be any points along that x-axis. Okay, so once again, invariant points are points that don't change after you perform a transformation. Okay, here, notice how the negative is inside the bracket. So that would be a negative b value, which would be a reflection along the y-axis. Okay, so now our y-axis becomes that mirror that we're flipping the graph along. Notice how you actually end up with the same graph, and that's just the nature of this particular graph. That won't happen with most graphs. So in this case, because we're reflecting on the y-axis, our invariant points would be any point on that y-axis. Okay, so this question here says, which transformations occur from figure 1 to figure 2? And then from figure 1 to figure 3. So if we look at figure 1 to figure 2, okay, you can see that reflection. So if I were to draw a line across that x-axis, you should see a reflection on that x-axis. Okay, now if I were to compare the graphs of figure 1 to figure 3, there's actually two possible answers here. Number one, you could say that there's a reflection on the y-axis to give you that graph in figure 3. Or you actually, in this particular graph, could say there's a translation and that the graph simply translated 2 units to the left. So on a test, both of those answers would be acceptable. Okay, so now we're going to look at a little bit of algebra. So it says the function f at x equals 5x cubed plus 10x squared minus 10 is transformed to each function below. Write the new equation. Okay, so this all comes back to function notation, and we just did 3 whole lessons on function notation. So when it comes to function notation, if your negative's on the outside, it's almost like you treat that negative like a coefficient, and you're going to multiply your whole f function by that negative. So I'm going to put that negative there, and then my f function is 5x cubed plus 10x squared minus 10. So really I'm distributing that negative to my entire equation here. So I end up with negative 5x cubed minus 10x squared plus 10. Okay, now in this case, and actually this is a typo, the negative's not supposed to be on the outside there. Okay, the negative's inside. So according to function notation and what we've done in the past, we're going to replace all of our x variables with that negative x. So I'm replacing my x cubed, my x with the negative x, and here as well. So all I'm doing is replacing the x's with the negative x. So here, if I cube the negative x, would it stay negative? Yes. So I'm just going to move it to the outside, so it becomes negative 5x cubed. If I were to square that negative, would it be negative or positive? It would actually be positive, right? If you square a negative, you end up with a positive because the negatives cancel out. So actually the sign would not change, and I'd still have positive 10x squared. And there we go. Lastly, we can actually reflect a graph on both the y and x axis. So in this case, I'm actually going to take my g function just because I've already replaced the negative, and that's probably trickier. So I'm going to take my g function. There it is. Oh, except for I should probably write j. And again, make sure you have your proper notation. And then I'm just going to multiply the g function by that negative, which means I'm going to distribute that negative into that g function. So then the negative times the negative becomes a positive 5x cubed. The negative distributed to the positive 10x squared becomes a negative 10x squared. And the negative distributed to the negative 10 becomes a positive 10. Perfect. Okay, so here is another diploma question. Please press pause on this video and see if you can figure out the answer. So it says, when the graph of y equals negative x squared is reflected along the y-axis. So go back to that little cheat sheet we made at the beginning of the lesson. So if it's reflected along the y-axis, okay, remember that would mean that the negative is inside your function brackets. Okay, so really we're going to end up replacing our x squared, our x, with negative x. So it looks like this. Okay, so in this case, I still have that negative on the outside. Remember, don't cancel because you have to apply the square first, right? Order of operations does kick in here. So exponents will always occur before multiplication. So then we have negative x squared plus 4. If you're wondering why is it negative x squared, well here negative x squared actually would mean I have a positive x squared here, but then the negative coefficient is still in front. So that's where that negative x squared comes from. So then the correct answer is B. Okay, and sometimes when I'm given a graph like this, I'll go ahead and graph it on my graphing calculator. And then I can just look and see and graph the new equation. In this case, it's the same thing. Does it look like it's reflected along the y-axis? Okay, so we're going to move to the next part of this lesson, which is reflecting on the line y equals x. So you will see this called as an inverse. Okay, so the key here is your reflection line is where y and x are the same. So really, it would be any point on your graph, so for example, where y and x are both the same values. So you can see that this line, this mirror line, intersects when x is 1 and y is 1, or when x is 2 and y is 2. So it just means when y equals x. Okay. The nice thing about this, it is trickier, but you will never get a question where you're asked to find the inverse or reflection on line y equals x, and then also perform another transformation. So these types of questions will always be separate to themselves. They'll never ask for multiple transformations when it comes to inverses. And you have to watch for that because in your workbook, you do get questions like that, but the curriculum clearly states that you will not be asked to combine functions when it comes to inverses. All right, so first of all, our invariant points, there are any points that lie on this line. Okay, so in this case, it would be any points where y and x have the same value. So I've seen this question come up several times, and I think I have one like this on your test, unless I end up changing it, but this one has shown up on the diploma. So if you had a random graph, like this one that I've drawn, if you wanted to figure out how many invariant points there would be, you would take your grid and you would just figure out, draw a line where x and y are the same. So we'll say this is 1, 1, 2, 2, 3, 3, and you would just extend that line, and wherever that graph intersects your line of reflection, that would be represent your invariant points. So we would have an invariant point here, 1, 2, 3, 4. So this graph would actually have 4 invariant points. Okay, so the inverse of a relation. So what ends up happening when you look at your mapping coordinates of an inverse, the y and the x just flip. Okay, so if your original graph had an ordered pair of 2, 3, and you reflected on that line of y equals x, your new graph would have an ordered pair of 3, 2. That's it. So because your x and your y flip, what ends up happening is your domain and your range would also flip. Now here's the trick, and you will get questions that ask this. Okay, your original graph could be a function, like the blue graph shown on the slide here. But after you flip that x and y, you could end up with an inverse graph that's not a function. So you can see this red dashed graph, the inverse graph, is not a function. And just in case you're rusty on what a function is, I know you guys covered that in Math 10C, but a function, it means that you should never have a repeated x variable or a repeated x value in your ordered of pairs. So here and here, I'd have an x value of 3. So I have 2 places on this graph with an x value of 3. So that means it's not a function. An easier way that most kids always remember is you can actually check it with the vertical line test. So if I can draw a vertical line and I hit this graph more than once, it means it's not a function. Okay? So here's a question, determine the inverse of the following graph. So I have AA, my original graph, my ordered pair would be, and I'm actually going to write my ordered pairs out. So the original graph would have an ordered pair of 0, 1. So that means my new graph, I would just flip them. So it'd be 1, 0. So 1, 0, there's my new point. B, my original graph has an ordered pair of 2, 5. So my new graph would have an ordered pair of 5, 2. And as I draw these points, I will connect the dots right away. If you wait till the end, you'll get confused on which dots to connect. So C, my ordered pair is -1, +4. So then that means, oh, I think I mixed that up. It's +4, -1, sorry. So that means my new graph would have an ordered pair of -1, +4. So I'd go over here, there it is, that's C. Okay, D would have an ordered pair of 8, 1. So that means my new graph would have an ordered pair of 1, 8. So I'm going to go to 1, 8, connect the dots. E, I have an ordered pair of 10, 1. So the new graph would have an ordered pair of 1, 10. There we go. So pretty simple. Determine of the equation of the inverse algebraically. So all you're going to do to determine the inverse is remember the x and the y, they just flip. So in your equation, if this is my original equation, all I'm going to do is flip the x and the y. So I'm going to replace the y with the x and replace the x with the y. And then from there, I'll just rearrange the equation to isolate that y variable. And there we go, there's my new equation. Okay, and you will see this notation for inverse. All right, so that f at x is -1, that means inverse. A lot of kids will mistake it for reciprocal, but because we're working with function notation, when you see that -1, it does denote an inverse of your equation or graph. Okay, so same thing. We are just going to replace the x and y, and then rearrange the equation for y. Remember, when you square root, you do need to consider both the positive and negative of that square root. So this would be my new equation. It's actually 2 equations. So it says a restriction on the domain such that its inverse is also a function. Okay, so if you were to graph the original graph of x squared minus 4, you would end up with a graph that looks like this. So this is a function, but the inverse would not be a function. The reason I know that is because this graph, if I were to draw a horizontal line, it would fail the horizontal line test. Okay, meaning that this graph would have y values that repeat. So this isn't the ordered pair, but just to kind of show you, if I had a y variable of -2, 5, which is not correct for this graph, and this was +2, 5, right? Then when I flip those, I'd have 5, -2, and 5, +2. So now, because I flipped them, I have x values that repeat, which means that new graph is not a function. So kind of an easy way to spot if your graph fails the horizontal line test, that means the inverse of that graph will fail the vertical line test, because those y values that repeat in the horizontal line test will become x values that repeat in the vertical line test. Okay. So if I wanted to write a domain, let me draw that again really quick. Okay, apply a restriction on my domain so that the inverse was, okay, a function. Really, I could pick any domain where I can't draw a horizontal line that hits the graph more than once. So this domain would be acceptable. x is greater than or equal to 0. Really, any domain, I could do x is less than or equal to 0, which would be this side of the graph. Any domain would work as long as I'm not, if I were to draw a horizontal line, I'm not hitting that graph more than once. Okay, so a domain that wouldn't work for this graph would be x is less than or equal to 2, positive 2, right? Because then I would be able to draw a horizontal line and I'd hit that graph more than once. Okay, so if the point 2, negative 3 was reflected along the following lines of reflection, what would be the new point? So the line y equals 0, remember that's your x-axis. The line x equals 0 is your y-axis, and the line y equals x is your inverse. Okay, and sometimes you can draw yourself a picture. So let's draw a picture here. If this is my original point, 2, negative 3, oh, right here, sorry. And if you were to reflect along the x-axis, it would be up here. So it'd actually be 2, positive 3, okay? If you were to take that point and reflect along the y-axis, your point would be over here. So it would be negative 2, negative 3. And if you were to take the inverse, all you're doing is flipping those points. So then you have negative 3, positive 2. Okay, so this is another diploma question. Which of the following is a function and also has an inverse that's a function? So let's start by looking and seeing which of these is actually functions. It looks like they're all functions. So which would have an inverse that's a function? So which of these would fail the horizontal line test? Because if they fail the horizontal line test, that means their inverse would fail the vertical line test. So this one's good, right? If I drew a horizontal line, I wouldn't hit that graph more than once. This one's not good because I can draw a horizontal line and it hits the graph more than once. This one's good because I can't draw a horizontal line, and this one's not good because I can draw a horizontal line right there where it levels off. All right, so there are some questions for you to try, and that's the end of this lesson.